Today we're going to be talking about types of acids, and we're going to be dealing mostly with the two basic definitions, one being an Arrhenius acid, the other one being a Bronsted-Lowry acid, and we'll learn how to identify the differences between these two. So let's get right into it. An Arrhenius acid, this is the type of acid that we kind of expect. This is going to be a substance that when we dissolve it in water, it's going to increase the concentration of the hydrogen ion, and this guy right here, there's our hydrogen ion. Something important to identify. So here's an example. Let's say we take HCl gas, we bubble it through some water that's liquid. What's going to happen is you're going to get ionization, and the concentration of the hydrogen ion is going to increase in that solution. You'll also get an increase in concentration in the chloride ion, but really we're after that hydrogen ion concentration, as we're going to learn later. That's really going to be what's going on with pH, but we'll get to that soon enough. Now, the Arrhenius acid and the Arrhenius base definition suits us just fine, but it doesn't suit us for all chemicals. But before we get into another type of acid or base, let's talk about an Arrhenius base. This is going to be a substance that when dissolved in water increases the concentration of the hydroxide ion. And there's our hydroxide ion right there. And anything, so something like sodium hydroxide, solid sodium hydroxide when placed in water, solid sodium hydroxide is going to once again ionize, and you're going to get the sodium ion aqueous, but you're also going to get that hydroxide ion aqueous, and that's going to increase our hydroxide ion concentration, again affecting pH, which we will talk about soon. Now, the Arrhenius acid and the Arrhenius base definition are very useful for us in chemistry, but they don't cover all substances, so we need to talk about another type of acid and base, and these are called Bronsted-Lowry acids and bases. And so let's talk about what these guys are. A Bronsted-Lowry acid is going to be any substance that donates a proton to a solution. Well, it turns out that a proton is just a hydrogen ion. You see, hydrogen ions, if we remember, have one proton and one electron, and when they lose their one electron to form a 1 plus charge, they become just a proton. Hydrogens don't have any neutrons. So a proton is just a hydrogen ion. So we could say that a Bronsted-Lowry acid is exactly the same as an Arrhenius acid. Both these substances donate protons or hydrogen ions to the solutions. Where it really differs is the Bronsted-Lowry base idea, because this is a substance that doesn't increase the hydroxide ion concentration, it accepts a proton. Okay, so there's the big difference. It accepts a proton, it accepts a hydrogen ion. And here's an example, and we're going to look more closely at this example. So if we look at the reactants HCl and water, what happens is when HCl is dissolved in water, the HCl will actually donate a hydrogen ion to the water. Once it donates the hydrogen ion to the water, what we get is what we call the hydronium ion. H3O1+. And we also get a chloride ion, which is what's left over. So we would say that the HCl acts as an acid and the water is acting as a base in this case. Now we're going to see that chemists often, and this is going to come up over and over, often just substitute the hydronium ion for the hydrogen ion. So if we see a hydrogen ion or a hydronium ion, let's not freak out. They basically mean the same thing. We'll get more into that later on. The next thing we're going to talk about is what a conjugate acid and a conjugate base is. Now, as we just mentioned, we said that a Bronsted-Lowry acid is anybody that donates a proton. And these guys are going to be reactants. And the conjugate base is going to be what is formed after an acid donates its proton. This is the product, kind of what's left over at the end after the hydrogen is gone. The base, again a reactant, is going to be whoever accepts the proton. And the conjugate acid is going to be what's formed after the base accepts the proton. It's the new product. So just to be real careful, we're going to have an acid and we're going to have a base as our reactants, and we're going to have a conjugate base and a conjugate acid as our products. And so let's talk about what does some of this look like and mean. First example, it says, give the conjugate base of the following acid. Now, remember, a conjugate base is what's formed after an acid loses its hydrogen ion. So if in this substance, hydrogen ion is given away, there goes their hydrogen ion. It's being given away to somebody else, a base. What's going to be left is going to be our ClO1 minus, ClO4 1 minus. It has a 1 minus charge because the 1 plus charge on the hydrogen canceled it out to give a neutral compound. So we would say that the conjugate base of HClO4 is ClO4 1 minus. Okay? Next example. It says, give the conjugate acid of the following base. So what a conjugate acid is, again, was going to be what is produced after it gains a hydrogen ion. So we're going to have the CN 1 minus, that cyanide ion, gain a hydrogen ion. So we could do something like this, and we can put those two together and crisscross the charges, so we get HCN. That would be considered the conjugate acid of the cyanide ion, which is the base. Okay, our next example, and it didn't give us any instructions here, but I'll give you instructions anyway, is going to be to ID the acid, ID the base, ID the conjugate acid, and ID the conjugate base in this reaction. And so in this reaction, we'll start right at the beginning here, and we can see that the HNO2 is turning into NO2 1 minus. And how it turned into it is it has lost a hydrogen ion. So that makes the HNO2 our acid, Bronsted-Lowry acid, and it makes our water our Bronsted-Lowry base. So remember, to identify the conjugate base, it is what's left over after the acid loses its hydrogen ion. So we would say that the NO2 is our conjugate base, and our conjugate acid is what happens to the base after it gains the hydrogen ion. So this would be the conjugate acid. Hopefully you can also notice that in this reaction we have a double arrow, leading us to believe we have an equilibrium occurring. So we could say in the forward reaction, HNO2 is acting as an acid, and that's just what we said. And in the forward reaction, water is acting as a base, and that's what we said. Now in the reverse reaction, the reaction that's going towards the left, notice that the hydronium ion is the one doing the donation of the hydrogen ion to the NO2 1 minus ion. So that's what makes it an acid, and we call it a conjugate because that's what was gained after the base from the reactant side gained a proton. And so that's another way to think of it. The next example shows a great example of a weak base being dissolved in water, and this is ammonia being dissolved in water. And so we're going to identify, once again, the acid, the base, the conjugate acid, the conjugate base. So if we start with the ammonia here, and we look what's formed, we form the ammonium ion. Now the only way we could have formed the ammonium ion is for water to be donating the hydrogen ion. And so if water does the donation of the hydrogen ion, water, in this case, is the acid, and the ammonium ion is the base. Okay? Now, after water donated its hydrogen ion, it became the hydroxide ion. That means this is the conjugate base. And the ammonium ion, NH4+, is what was left, or what was produced after the base in the reactant side gained a hydrogen ion. So this is our conjugate acid. Okay, and so in our reverse reaction, let's look at a reverse reaction just to double check everything's going all right here. In our reverse reaction, the ammonium ion is the one donating the hydrogen ion. So that's what makes it the conjugate acid, because acids donate and bases accept, and the hydroxide ion is what accepted. Okay, so that is our quick little talk today on Bronsted-Lowry acids and bases, and there's going to be some practice problems that go along with this.